Assalamualaikum warahmatullahi wabarakatuh and very good day Dr. Sharil. So we are going to present to you about our Project 1 which is Satellite Attitude Control System. And our fellow team member is me, Muhammad Amai Famil Oman, Wan Mahdi and Nur Iman Zaini.
Assalamualaikum. So my name is Wan Mahdi bin Wandawan and my metric number is 171771. So right now I'll give you a, a brief introduction about our project, which is satellite altitude control system. But first of all, we need to know what is control system. So control system are tools and algorithms that designed to manage system behavior and design performance. This is to ensure efficiency, accuracy, and stability in dynamic condition. Now, what is satellite altitude control? Satellite altitude control is a precise orientation of a satellite to a specific point in the sky. This is one of the common approach is the active three-axis altitude control in modern spacecraft. There are many types of altitude control systems. One of them is momentum management based devices and momentum exchange based devices.
Hello, and my name is Nur Iman bin Zaini, and for my part, I will be explaining the literature review for this report. So, first of all, we start with the historical background of the satellite attitude control system. So, on 1957, our artificial satellite is launched out in the space. So, at the time, our satellite attitude control system relies on passive stabilization, and on 1990s, the active attitude control system were introduced. Then due to more advanced material, the satellite control system attitude control system have been advanced, and with more advanced material, sensors, and improved ACS significantly. So the importance of ACS is to provide the spin axis stabilization to proceed with the certain satellite mission. Okay. For example, Hubble Space Telescope is to maintain precise orientation for capture high-resolution astronomical images. Next.
Now I'll talk about the system description. So the satellite altitude control system is an essential element for controlling and preserving a satellite's orientation in the orbit. The satellite's rotating position with respect to an external reference frame, such as the Earth, stars, or other celestial bodies, is referred to as its attitude. Whether for communication, observation, or power generation, the ACS makes sure that the satellite's instrument, antennas, or solar panels are orientated correctly to carry out their designated tasks. There are many systems in satellite altitude control system, control system, such as sensors, and there are many sensors that we can see here, which is such as star trackers, gyroscope, sun sensors, and magnetometer. Other than that, controller, the sensor input is processed by the controller to determine the required adjustment, which can reduce the deviation from the intended rotation algorithm, like the proportional integral derivative (PID), nonlinear control, or sophisticated resilient control approaches like H control produce directives. Other than that, actuators which apply corrective forces or torques to achieve and maintain their desired attitude. Uh, for example, the reaction wheel, magnetokers, and thrusters. Uh, and lastly, feedback loop. Feedback loop is the closed loop design for the ACS, which ensures accurate correction and reduces orientation mistakes by continuously informing the controller about the system's performance through updated sensor data.
So I will present to you about the control strategy for the satellite attitude control system. So there's a 6 control strategy in the ACS, which satellite attitude control systems. So first and foremost is nonlinear control. So the application for nonlinear control is large altitude maneuvers significant external disturbance. So the technique applied for this nonlinear control is feedback linearization and sliding mode control. So this feedback converts nonlinear system into simply linear ones, and sliding mode control handles uncertainties and disturbances effectively, especially in the presence of aqueous saturation. So this advantage is ensure reliable performance is challenging real-world conditions with nonlinear dynamics. So the second is linear control. So the application for linear control is more altitude correction where linear approximation are sufficient. So the technique applied is linear quadratic regulator, which optimize the control action based on state space representation. An advantage is ideal for safety state tasks like maintaining geostationary orientation. So the third one is fuzzy logic control. So the application is high uncertainty or poorly modeled satellite dynamics. So the principles that we, ap- we apply is utilize the qualitative rules. Examples, if error is large, apply high torque. So the advantage is robust against the imperfect data offers computational simplicity. So the fourth one is H infinity control. So the application is robust control in environment with significant disturbance. Examples, low Earth orbit (LEO). So the features is minimize worst case effects of uncertainties and disruptions. So the advantages is ensure stability and performance even with model inaccuracies or several external factors. So the fifth PID control. So PID control which proportional integral derivative control. So the application is simple attitude stabilization task. So the principles that we use for this PID control is proportional P, integral, and derivative. So for proportional is correct current errors, and for integral address accumulated errors, and derivative D predicts future error. So these advantages is simple, reliable, and effective for reaction wheels and thrusters. Last but not least is other advanced techniques, which are model predictive control (MPC), adaptive control, adaptive controls, and bank control. So the for model predictive control (MPC) optimize control action for precise trajectory planning and energy efficiency. And for adaptive control is adjust parameters dynamically to accommodate changing satellite properties. Examples, fuel depletion. And bank control is one of the control for scenarios like satellite detumbling where continuous control isn't feasible. So that's all from me. Thank you. So I will present about the block diagram for satellite attitude control system (ACS). So this diagram represent the control loop of a satellite attitude control system. So here's an explanation of each block. So desired attitude, the target orientation the satellite aims to achieve. An error detector compare the desired attitude with the actual attitude to compute the error signal. So the controller they process the error signal and determines corrective actions to minimize the error. So the fourth one is actuous. Device examples like reaction wheels, thrusters execute the control commands to produce corrective torques. And the fifth one is satellite dynamics. As you can see, the explanation is the satellite physicals response to the applied torque, altering its attitude. And last but not least is sensors, measure the satellite current attitude and provide feedback to the error detectors for continuous connection. So this closed loop ensures that precise attitude control by constantly adjusting based on the feedback. And this there's some explanation or the summarize for this figure 1.1. So as you can see, the error detectors compares the desired the actual attitude, generating an error signal, and the controller process it actuals apply corrective torque, and sensors provide the feedback for constant adjustment. So this can ensure the precise satellite orientation for accurate instrument, antenna, or solar panel operation. So I think that's all for me. Thank you very much.
I'll be explaining briefly about analysis based on literature. So ACS system, it need multiple strategies for it to function, for it to meet specific requirements such as stabilization, robustness, precision, and energy efficiency. So um, the situation in the outer space is complex. Some maybe they will be stable condition, but sometimes it will be complex situation. So that's why we need multiple strategies for it to function efficiently. For example, PID is more into simple and low cost requirement, but it only suitable for stable condition only. However, for non-linear control excel in dynamic environment, but the demands in significantly computational demand. For fuzzy logic is robust, but too uncertain and sacrifice precision. For H infinity provide high robustness, but it complex to resources and intensive. And for MPC offer adaptability and constraint handling, but it require at a high computational cost. Thank you.
In conclusion, in dynamic situations, the ACS are essential in ensuring precision, stability, and operational effectiveness of the spacecraft. Other than that, the choice of ACS depends on mission needs, complexity, resource constraint, and environmental consideration. And for the future trends in ACS, there must be increased use of hybrid and intelligent control methods, enhanced capabilities due to advance in computational power and adaptive algorithm for higher precision and efficiency in satellite operations. Thank you. That's all from us. Thank you.